Hello, Calculus 2. I'm moving in here to section 10.4 where we learn about polar coordinates. So let's see how far we get here. There's a lot to discuss. Section 10.4, 10.5. There's a lot of good things about polar coordinates. So we'll just do a short video here, but it's a whole new coordinate system. And so instead of the XY coordinate system, we have a new coordinate system. We have a pole and we have a polar axis. And what we do is if I want to get to any point in the plane, it's still a two-dimensional plane, I stand at the pole and I rotate counterclockwise like an angle does in standard position. I rotate an angle theta and I walk out a distance r, and that'll get me to any point in the plane. And we call that point r theta. I guess I said kind of do theta then do r, but you could walk out r then rotate theta. But we order the ordered pair r theta. But that'll work. Now, I mean, do you understand that that'll work? Convince yourself that this system will get you anywhere you want to get in the two-dimensional plane. Like if you wanted to get here, I want to get to that point. I could rotate a negative angle theta, of course, and I could walk out this big long distance r, and I would get there. Can I get here? Yeah, I can rotate theta and walk out r. I can get anywhere. Can you get right there? Yeah. Walk out r, rotate that theta. The funny thing about polar coordinates is there's a couple ways to get there. What did I say? To get here, I had this negative angle theta and I walked out r. You know, I could have went around this way theta and walked out r. I could have went around an extra time and got here with a big theta over 360 degrees and walked out r. So there's a lot, sometimes there's more names for a certain point. Now, it's getting kind of messy here. Now, the truth is, I tried to do this without an x and a y axis because we're in this new coordinate system, r theta. But really, it's convenient to kind of superimpose this on the x and y axis. It really is. So, because, the x and y axis are nice 0 degrees, 180 degrees, 90 degrees, 270, So it's cool to kind of have the x and y axis in the background. You put the pole right here at the origin. And also what happens when you do this is you see the relationship between r and theta and x and y. Because that's what we got to do. We got to convert back and forth sometimes. So here we go. If I was out here at this point, one way to get there is I go over x and I go up y. That's the old rectangular coordinate system. Over x and up y, and you get to this point. The new system is stand at the pole, rotate an angle theta, walk out a distance r. And so what happens is you have this right triangle, and therefore from this picture, and I would advise you to learn this picture and understand this picture, it's easy, and a little bit of right triangle trig, and the relationships from x and y to r and theta are beautiful, that you see them quite clearly here. Here's one. X squared plus y squared is r squared. That's true. The tangent of theta is y over x. Or sometimes that's stated as theta is the tangent inverse of y over x. Of course, you always got to be careful with tangent inverse. It has that restricted range. It gives you an angle in quadrants 1 or 4, and sometimes theta is actually in 2 or 3. You got to be careful with your calculator and that tangent inverse button. But that's true. Here's another true fact. X equals r cosine theta. Maybe that wasn't super obvious to you there. Let me just say it like this. What's the cosine of theta? The cosine of theta is adjacent over hypotenuse, x over r, and if you multiply to the r to the other side, x equals r cos theta. Cool. Similarly, y equals r sine theta. So there you go. That picture, these equations relate x's and y's to r's and thetas. If I gave you r's and thetas and I wanted you to convert to x's and y's, I think you'd use these. If I gave you x's and y's and wanted you to convert to r's and thetas, I think you'd use these. But you use these formulas to convert back and forth. But then once we convert back and forth to kind of get used to things, and then we just kind of try to work in our new coordinate system, polar coordinates. They're useful for a lot of things in Cal 3, and here they are, the last topic here in Cal 2. So one of the, here's, we do this. Negative 1, 1 is a point in rectangular coordinates. Convert to polar. So I'm converting a point into polar coordinates. So that's pretty easy. So I could look at this picture. Well, anyway, I'd go off this picture. Negative 1, 1. I could draw my own picture. Is over here, negative 1 and up 1. There it is. And then what I need is that R. I've put this question on a test, and thousands of students will tell me R is 1. So don't do that. If I go over 1 and up 1, I can use Pythagorean's theorem to find R. Negative 1 squared plus 1 squared is R squared. 1 plus 1 is 2. So R is the square root of 2. That's the hypotenuse of that triangle. Or that's that distance. Cool, we just found R. It's the square root of 2. I want to find theta. Well, according to my little formula, the tangent, I could look at the picture and come up with my own formula, but I could memorize these, or these are memorized formulas, or they're pretty darn obvious from the picture. So I'm looking for the angle theta, which is the y over the x. Hang on, the y was a 1, the x was a negative 1, so the y over, it's just a negative 1. The tangent of theta of negative 1. Okay, my calculator does tell me negative 45 degrees. By the way, we should talk in radians, so I'm going to say negative pi over 4. But that's not the angle. That the calculator told me that. But that's over here in quadrant 4. And you know that I'm really, based on the picture and based on where I am, I'm in quadrant 2. So actually that angle is a 45-degree angle in quadrant 2. That is 135 degrees. So that's not the answer. That's the related angle or reference angle. The actual answer is 135 degrees, or 3 pi over 4. Cool. So the question was, give me a point in polar coordinates. So R theta, square root of 2, 3 pi over 4. Good job. The truth is, when I put this question on a test or a quiz, I say, give me 4 different names for this point. Because the truth is, again, this is kind of funny. It doesn't happen in rectangular coordinates. That's the unique name for that point. But in polar coordinates, this point has several names. Based on the cyclical nature of angles, I've got a lot of names I could name it. I could name it negative, that angle, negative 5 pi over 4. Use that negative angle, and it lands there, and then I walk out that distance, square root of 2. When I found R, I didn't put plus or minus. I feel like R is a positive distance. You walk out from the origin, the square root of 2. But the truth is, there is a way to have a negative value for R. And what you do is you rotate, like you're about to, if R is negative, you don't walk out that distance. You rotate that angle and you walk backwards that distance. So you can walk backwards the distance negative R. So using negative square root of 2, could I come up with a name? Let's see. So if I had negative square root of 2, that means I want to go to this angle. Yeah, I do. Now I want the negative pi over 4. If I go to negative pi over 4, but then walk backwards negative square root of 2. It's like I'm staring out this way, but because R is negative, I walk backwards negative square root of 2. That lands me in this point. That's the point I'm trying to get to. Can you give me another name for it? Negative square root of 2. Let's see, how about if I name this angle 7 pi over 4? 7 pi over 4 is the name of the angle. It lands here. I walk backwards negative square root of 2, and that puts me at the same point. So there's multiple names for a point in polar coordinates. Converting points isn't that fun, but it gets you going and gets you using these formulas a little bit. What I really like to do is convert equations. So here's a famous equation. let's go ahead and start with something good here. X squared plus y squared equals 9. Now, we could talk about what that is. Earlier this chapter, we talked about what that was. That is a circle, radius 3, centered at the origin. It is a circle, radius 3, centered at the origin. I don't really need a picture of it. My question is, convert that equation into polar coordinates. So that's the rectangular equation, and the polar coordinate equation would be if I convert. Well, it's super easy. Some of you might be thinking I should take the x and replace it with this. I should take the y and replace it with this. I could. That would work. But I see something that shortcuts that a little bit. Right there, x squared plus y squared is r squared. So how about r squared equals 9? And the truth is, as soon as you replace x squared plus y squared with that r squared, you have converted to polar. But just like with x's and y's, we often like to solve for y as a function of x, although I don't have that here. I like to solve for y. I like to solve for r as a function of theta. So if I solve for r, I take the square root and I get plus and minus 3. You know what? I'm just going to use the positive 3. I'm just going to use the positive 3. And anyway, what is this? In polar coordinates, this is the polar coordinate equation of a circle of radius 3, centered at the origin. Let me make a connection here. Way back in 3rd or 4th grade, when someone said, hey, let's graph y equals 5, and you would plot points. Come on, kids, let's plot some points. And you would go, when x is negative 3, plug it in, what do you get for y? And you'd say, y is 5. Y is stuck on 5. What about when x is 0? Y is 5. What about when x is 1? Y is 5. And the point is, x can be whatever it wants. X gets to be sort of arbitrary. Or it takes on all values, and y is stuck on 5. That's what happens in this rectangular equation. And then visually, what that means is, x gets to be whatever it wants while y is stuck on 5. So you get this horizontal line, y at 5, y equals 5. Well, the analogy to polar coordinates is, I think, kind of interesting. Again, if I made a little chart to plot points, theta and r, theta can be whatever it wants. Theta can be whatever angle it wants to be, and r is stuck on 3. And visually, theta gets to go round and round and round and get to be whatever angle it wants, and r is stuck on 3, creating a circle of radius 3. I mean, I don't know. That's my way of explaining it. I mean, this explained it already, but I just wanted to plot points and see what this is. It's a circle of radius 3. It's obvious. And it's easy. And circles have always been a bit of a pain for us in rectangular coordinates. So now, circles are sweet in polar coordinates. Look at that equation. R equals 3. So, circles are nice. In this new coordinate system, polar coordinates. Not everything's nice. Let's try something else real quick. This is a line. Y equals 3x plus 5. That's a nice line in rectangular coordinates, slope of 3. In polar coordinates, lines aren't the best thing. You can do it, though. If I want to convert this, I think I will replace y with r sine theta. That was in my notes from 2 minutes ago. I think I'll replace x with r cos theta. And the truth is, I'm converted. Okay, I was a Methodist, now I'm I'm converted. I was in rectangular equation, now I'm in polar equation. I'm converted. But we like to solve for r. Let's see here. I think I'll subtract this to the other side. R sine theta minus 3r cos theta equals a 5. Factor out the r. Sine theta minus 3 cos theta in parentheses equals 5. Divide by that. So to solve for r, this is your equation of a line. This is your equation of a line in polar coordinates. It is that line. So maybe lines are better in rectangular coordinates. Maybe they're not so fun in polar coordinates, but they work. They can work. You can convert back and forth. That's not enough for now. There's a lot more to talk about. We're just getting introduced to polar coordinates. You can try some homework. Thank you.